Alright, so we are going to go over study guide 5. It's about benzene and aromatic compounds, chapter 15. Alright, so let's talk about the structure of benzene and how we can write its name. So let me switch it. Alright. Alright, so let's draw benzene ring. We can call benzene ring. So it's basically, this is a benzene where it is alternate single bond and double bond, single bond and double bond, and single bond and double bond. And this carbon is sp2 hybridized and it's 120 degree angle. So once it's a sigma bond, single bond is the sigma bond, and then double bond, which is one sigma and one pi bond. This is the orbital diagram. You can see the double bond, how they forms. This pi electron overlap, they float. So that's how they have three alternate single bond and double bond. All right. So, all right. Now, let's find some common names, and they are frequently used than the IUPAC name. This benzene ring and on the top of CH3, this whole entire molecule is called toluene. This benzene ring on the top of it, OH, it's phenol, it's called phenol. This benzene ring on the top of its NH2 group, which gives aniline, name is aniline. The benzene ring with the CHO, it's benzaldehyde. Benzoic acid, COOH, group on benzene ring, it's called benzoic acid. CN, benzonitrile. OCH3 attached to benzene, anisole. COCH3, acetophenone. CO and then surrounding there is a benzene ring, so benzophenone. So those are commonly used. Now monosubstituted benzene. So we name in the ways as the other hydrocarbon with benzene as a parent name. For example, this Br is joined with benzene ring, so we can say bromo benzene. So that is bromobenzene, and so benzene is a parent and bromo is a substituent. This one is propyl benzene. The structure we draw, this benzene with propyl, so it's propyl benzene. So alkyl substituted benzenes with alkyl substituents smaller than ring, name as alkyl substituted benzene. So that's the rule. Now, alkyl substituted benzene with alkyl substituents larger than ring, name as a phenyl substituted alkane. So for example, if it is benzene attached with this hydrocarbon, there is 1, 2, 3, 4, 5, 6, 7 carbon chain. So it's heptane, and on the 2 carbon there is a phenyl group. So that's why 2-phenyl heptane. So we can name it monosubstituted benzene. Alright. Now di-substituted benzene. So when there is a di-substitute, more than one substituents on a benzene ring, then we can use ortho if 1 to 2 relationship. This is ortho position. This is benzene ring, and on 1 and 2 position there is X and Z substituents, for example. So that's called ortho. If it is 1, 2, 3, 1 and 3 position, they are located, those substituents, then it's a meta substituents, meta relationship. And this is a para 1 and 4. 1, 2, 3, 4. So it's a para. So when we draw meta-dichlorobenzene in here, so whenever you heard meta, it's 1 and 3 position. So 1, 3 so it's instead of 1, 3 dichlorobenzene, you can write meta-dichlorobenzene. This is orthobromoaniline. So this is 1 and 2 position. So it's ortho position. Draw para-nitrobenzaldehyde. So we have 1 and 4 position. 1, 2, 3, 1 and 4 position. So we can say para-nitrobenzaldehyde. Alright. So when toluene is, let's go back. Alright, so when toluene is reacted with Br2 and FeBr3, then a bromine gets added to the ring and the reaction occurs at para. So we need to draw this product. So Br2 and FeBr3. In that one, we got para-bromotoluene, or we can say 1-bromo-4-methyl benzene. So that's where you can write. Alright, next is more than 2 substituents. There are some rules and we will apply to some of those examples. Okay, so number the rings to give the substituents the lowest number possible. List substituents alphabetically when writing the name. Toluene, phenol, aniline, benzaldehyde, benzoic acid or benzonitrile can serve as a parent. Then principal substituent CH3OH, Na2CHO, COOH, those are the substituent groups. They are given the number 1. Let's say we need to draw 4-bromo 1,2-dimethyl benzene and TNT 2,4,6-dinitrotoluene. So in this one 4-bromo. So whenever this is a benzene ring 1, 2, 3, 4. So this is 4-bromo 1,2-dimethyl benzene. So this is the perfect structure. Now trinitrotoluene. This whole entire thing is toluene structure, but 2, 4, 6 trinitrotoluene. Metabromotoluene. This is a toluene structure 1, 2, 3. 1 and 3 position is bromo, so that's why bromo. Metabromotoluene. Isobutyl benzene. So this is a isobutyl and that's a benzene ring. So that's isobutyl benzene. Alright. So that's where when we practice more, you will get a better idea that how you apply the rules. Okay. Alright. Let's work on next one. Alright. So when you have these groups, this CH3 on 1 and 3 position, it's a metamethyl toluene or metadimethyl benzene. Alright, 3-methyl toluene and 1,3-dimethyl benzene. So you can name it accordingly. This is butyl 1, 2, 3, 4. So it's beta hydroxybenzene, and you can name it various ways. This is 4-bromo. This is 4-bromo 2-chlorotoluene or 4-bromo 2-chloro-1-methyl benzene. So the phenyl group is often abbreviated as PH. Thus phenol, let me erase it and scroll it down so you will see that. Alright, so phenyl group is often abbreviated as PH. Thus, phenol can be written as PHOH and benzoic acid can be written as PHCOOH. Formal amino group, hydroxy group, nitro group, and when it's joined with those R chain, then you can see formal group or an amino group or hydroxy or nitro, so and so forth. So that group you can name it accordingly. So these are the name of the group, and when it's attached, then you can name it accordingly. So let's see how we can name phenol. In this one, phenol serves as a parent. So first we need to identify parent chain or parent one. Then use ortho-meta-para for a di-substituted ring. If more than two substituent, number the rings. OH is often the number 1, another substituent given the lowest number possible. List substituents alphabetically when it returns its name. For example, this meta and this is nitrophenol. Alright, so meta is direct position, nitro direct substituents, and phenol is a parent. So this is meta-nitrophenol. There are some of the names that we are going to apply. Metaformal phenol. This entire one is phenol, but it's on the 1 and 3 positions, so more metaformal phenol. Or you can say meta-hydroxybenzaldehyde, or you can say 1-formal 3-hydroxybenzene, or you can say meta-formal hydroxybenzene. So there are variety of ways you can name that. This is toluene. The whole thing is toluene, benzene on the top of CH3, but this is ortho position 1 and 2. So it's orthoaminotoluene or orthomethylaniline or 1-amino-2-methyl benzene. So you can name accordingly. This you can name it as a bromo. This is basically para 3-methyl bromophenol. So you can name it, or you can name it 1-hydroxy 4-bromo 3-methyl benzene. You can name it either one. This one is para-nitrobenzoic acid. This is a nitro group on this benzoic acid, so that's why it's para-nitrobenzoic one. So you can, when you practice more, you will answer di-substituted with finding its name. Alright, let's go to next one. Okay, next page. Spectroscopy. Some characteristic spectroscopy absorption of benzene derivatives. IR spectrums CsP2H, that is 3150 to 3000. Okay. Then C double bond C 1600 1500 centimeter. 1H NMR for benzene 6.5 to 8 ppm. Benzoylic H, you can see these are the range given basically, and you try to memorize and apply reading the graphs. So proton from the benzene ring is highly de-shielded, showing characteristic signal in 1H NMR around 6.5 to 8 ppm. Electron withdrawing group will shift the signal downfield, while the electron withdrawing group will shift the signal to the higher chemical field. So that's why 13C NMR can be used to determine substitution pattern in di-substituted benzene. So when you practice, the formula. So here you can see propose a structure consistent with this data. Molecular formula given, IR absorption, H and MR data is given. So whenever H and MR 3H, you can see 3H can see 2 H's. This is 2 H's. 2 H's can see 3 H's. So this refer to H in the benzene ring. When this one refer to H in the benzene ring, so that means when you apply CnH2n plus 2, we can say C8H10O, C8H18. Now remember, 8 plus is 4 degree of unsaturation. So when you decide the structure, it could be, this is the structure instead of X, we can see this is the structure we propose. You have a sample of compound, molecular formula C11H15NO2 that has a benzene ring substituted with 2 groups, CH2N, CH2, CH2, CH3, and it exhibit given 13 NMR, 13 CNMR. What dice substituted benzene isomers corresponding to C13 data? So you can see those signal 1, 2, 3, 4, 5, 6, 7, 8. Those are the ones. And remember, there are 10 signals. So when you have these structures, you number the carbon. There are total 10 signals in that structure. But when you draw this structure, given this formula, you also get 10 signals. But here we got only 8 signals. So we try to be more creative and draw these structures, and you get total 8 signals. So this will be the best choice. Alright. So benzene is basically very stable because it forms the resonance. Double bond could be here, 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 or here, here, here. It's 1, 2, 3, 4, 5, 6. Or it could be between 1 and 2 carbon or 2 and 3 carbon, the double bond. So it's basically floating. The double bonds are floating inside the ring. And describe the real structure, hybridized one. So it's a carbon is sp2 hybridized, all bonds are equal, describe 1.5 bonds. And that's why we do that. This is the hybrid one, alternate. Double bond floats inside. What is the consequence of resonance stabilized double bonds? Different reactions. Do you remember the reaction of cyclohexane with Br2? And it is electrophilic addition reaction. So what do you think? This double bond is going to break and forms the Br is here and Br is here. So addition product. Now benzene will usually do not go substitution. Addition is easy, but substitution usually they don't go. The carbon-carbon double bonds are too stable, too hard to break those double bond. So instead there will be substitution reaction. The benzene Br2 yields bromobenzene. So Br2 and FeBr3, you can add Br2 here. It's a substitution. Remember, benzene is everything is planar. It's a cyclic, it's conjugated, and 6 pi electron system. So that is Huckel's rule, aromaticity follows the aromatic compound. So benzene is a conjugated compound. It is aromatic compound, and aromatic compounds are planar, flat surface, no chair compounds, cyclic compounds. They are ring closed, conjugated, sp2 hybridized, and total 4n plus 2 electrons where n equals 0, 1, 2, 3, 4. If those things follow, then it's an aromatic compound. If it has 4 and pi electrons, it's anti-aromatic. If it is missing any of the above, it's non-aromatic. So that's the Huckel's rule, and you need to apply that. Now, which of the aromatic compounds? So based on this rule, we need to identify aromatic, anti-aromatic, so on and so forth. And for nitrogen and oxygen in the rings below are sp2 hybridized. We need to determine how many electrons of each of them in the p orbital and their participating pi bonding. So in this one, 4 pi electrons, so anti-aromatic, no. In this one is 8 pi electron, 1, 2, 3, 4, so it's anti-aromatic. This is 1, 2, 3, 4, 5. This is naphthalene. This is 14 pi anthracene. This is pyro, and that is not aromatic. Cyclopentadiene, that is not aromatic. Pyridine, 1, 2, 3, yes. Furan, 6 pi electrons. You consider 1, 2, 3, 4, 5, 6. Okay. Imidazole, that is 6 pi electrons, and that is aromatic. Pyrimidine, 6 pi electrons, and cyclopentadiene, 6 pi electrons. So that's where you can find electronics, aromatics or non-aromatics. Nitrogens and oxygen will change their hybridization to create aromatic compound. Where are the lone pair electrons in pyrrole, pyridine, imidazole, and pyrimidine? They will contribute to the conjugation and if needed, pi bond counts. So now what do you need to recognize aromatic compounds? The reason why it is important to recognize aromatic compound, it is because of their unusual stability. They are stable and they affect their reactivity. For example, most hydrocarbons are not acidic. pKa is greater than 45. But cyclopentadiene is actually acidic as water. Why? To answer the aromaticity, you need to find which one is stable. How good is this acid and how good stable it is? So anti-aromatic compounds, basically they are also planar, conjugated, but they do not have 4 and pi electron system. And these compounds are very unstable. So that's why it's anti-aromatic compound. So for aromatic compounds, compounds are not too planar, do not give 4n or 4n 2 pi electrons in the pi orbitals. Alright, so not aromatic compounds, this is not aromatic compounds one. Alright. Now when you practice, you need to, for the molecules below, predict whether the molecules will expect some aromatic character or not. In here, yes, this is 1, 2, 3, 4, so it's 4 and pi, yes. This is 6 pi, so no. This is 4 pi, no. This is 6 pi electrons. And it considered carbocation provides conjugation and lone pair provides conjugation and 2 pi electron system. Now which compound is stronger acid and explain. This is 6 pi electron, this is 4 pi electron. So donating a hydrogen in this structure, specifically this structure, forms aromatic compounds which is then more stable than anti-aromatic compound formed in other structure. Alright. Now draw the resonance structure. So again, when there is a pi electrons, the flowing of these electrons in the directions. Alright. So when you see the resonance forms, when it floats, the resonance forms. So always move negative charge when you draw a resonance. Explain why compound A is much more stable than compound B. Remember, aromatic more stable, anti-aromatic less stable. So you can see this is 1, 2, 3, 4, 5, 6 and total 8 pi system. This is 6 pi system, the anti-aromatic. And these are some problems that you can work on it at your own pace. We finished the study guide.